Hi everyone, thanks for joining us for Coding Practice with Kickstart. My name is Lizzie and I am the Kickstart Program Manager. We hope you enjoyed practicing our problems during the session and learned something new to kickstart your coding competition journey. Throughout this video, we'll hear from various Google engineers on how you can go about solving each of the problems you just attempted. Regardless of what you solved, we hope these walkthroughs will provide some helpful tips and tricks to use for future competitions. If you're watching this video live, feel free to ask any questions to our Google moderators in the chat feature below. Now let's hear from some of my colleagues who will walk you through the problems from this week's session. Take it away.
Hi everyone, my name is Shubham. I work at Google as a software engineer. I work on Google search and volunteer for Kickstart whenever I have time. Today I am going to walk through the record breaker problem. Before starting with the problem, I would like to give an advice. Always read the problem statement very carefully, taking your time through it. Also pay special attention to the input and output section as they give you an idea about the expected time complexity. Now we will start with the problem. Isyana is given the number of visitors at her local theme park on consecutive days. A day is record breaking if the number of visitors is strictly larger than the number of visitors on all previous days. If it's not the last day, then the number of visitors on the day is strictly greater than the number of visitors on the next day. First and last days can also be record breaking. Now we need to find the number of record breaking days. If you look carefully, this problem lends itself to a visualization problem. It is always good to keep some scratch paper on hand while participating in the competition. So now we are going to draw a graph using one of the samples present in the problem. In this graph, the x-axis represents the days, y-axis represents the number of visitors. If we observe this graph carefully, we can easily spot the record breaking days. Day 1, 3 and 6th are record breaking because the number of visitors is greater than the number of visitors on all previous days as well as greater than the next day. So they satisfy both the condition, that is why they are record breaking. Day 2 is not record breaking because the number of visitors is less than first day. It violates the first condition, therefore it's not a record breaking. Similar is the case for day 4, 7 and 8. They don't satisfy the first condition. Though day 5 satisfies the first condition, but it violates the second condition because the number of visitors is less than the 6th day, which is the next day. Now we can easily come up with the algorithm to solve this problem. To check whether a particular day is record breaking or not, we need two things: maximum number of visitors on all previous days and the number of visitors on the next day. Now we will start looking into the code for this problem. If you are not sure how to start writing your code, recall that there are code snippets present in the FAQ section that show you how to read from the standard input and write to standard output. I am going to use C++ to solve this problem, but you are free to use any of the language which is supported on the platform. This is the skeleton of my code where I am reading from the standard input, writing to standard output. I am using an array to store the number of visitors. This is my core where the entire algorithm is present. I have used two variables. Previous record maintains the maximum number of visitors seen till now. Record break contains my answer, that is the number of record breaking days. Now I start looping through the array and check for each day if the number of visitors is greater than previous record, that is the maximum number of visitors seen till now, and the number of visitors is also greater than the next day. If both the conditions are satisfied, I increment record break count variable, which is the answer. The last step of the loop is to update the maximum number of visitors seen till now, that is variable previous record. One of the common mistake in these type of problem is accessing out of bound indexes like -1 or n. If you attempt this on the platform, it gives the runtime exception. One of the possible scenarios in which that can happen in this solution is, suppose the value of I is equal to n-1, then the condition present in the red box will try to access nth element of visitors array, which does not exists, so it gives array out of bound exception. To avoid such exceptions, I will explicitly handle the first and the last index. It is always good to build and run your program on local ID or online ID to see the detailed error. And that's all the code together. I hope you enjoyed the problem. Please make sure to check out the full analysis on the dashboard. Also, please stay tuned because my colleague Daria is going to walk through the next problem we will walk. Thank you.
Hi everyone, my name is Daria and I'm a software engineer at Google. I work in the Privacy and Data Protection Office, and in my free time I help out with Google's coding competitions. We hope you enjoyed all of the problems from our session. Today I'm going to walk you through the problem Wiggle Walk. Let's begin with the task description and limits. You are given a grid with R rows and C columns and a robot, which can move in 4 directions. When the robot is instructed to move in one of the 4 directions, it won't stop until it reaches the unvisited cell. The task is to find a cell where the robot stops after following given instructions from the starting point. Limits for the number of tests, moves, and the grid size you can see on the slide, as well as time and memory limits, as stated in the problem statement. The first idea that you might think of is to do exactly what is described in the task. We create a grid as a 2-dimensional array. For each cell, we set a Boolean value to true if the cell was visited, and false otherwise. On the slide, you can see how the table will look like for the sample test. Processing each instruction, we use a while loop to continue moving until the robot is positioned on an unvisited cell. The Python code might look like this. The dictionary deltas here is a great way to avoid several if-else conditions for different instructions. I always use this approach for tasks where something is happening in the grid. This solution works correctly. But what happens when we submit it to the testing system? We get memory limit exceeded on the first test set. The reason is the size of the created 2D array. When the number of rows and the number of columns are maximum, our 2D array takes more than 1 GB of space. So, maybe we don't need the full grid. The robot visits only n cells. What if we keep only this? Let's slightly change the implementation by replacing the array with a dictionary or map in other programming languages. Now we create a cell only if the robot visits it. Arrows on the slide show changed lines. Now when we send the code to the testing system, it passes the first test set, but we receive a time limit exceeded for the second test set. The space complexity is now big O of n, but the time complexity is big O of n squared. Let's see why. For some instructions, the robot needs to make several steps until it reaches the unvisited cell. Imagine the robot gets an instructions like east, west, and so on. So it goes left and right, and with every instruction, the visited segment grows. The total number of steps for this test will be big O of n squared. In our implementation, the robot needs to visit each cell of the growing segment every time it processes an instruction. But what if the robot can just remember where the segment starts and ends, so it can just jump right to the next unvisited cell? Let's say the robot goes from cell C to cell D. For both cells C and D, after this step, we know the next unvisited cell in one direction. We know that if the robot needs to go from cell C in the same direction again, cell D was already visited, so the robot should jump to the cell E. For cell D, we know that cell C was already visited, which means that the robot will stop in cell B if it goes in the opposite direction from cell D. In the table, we will now store possible jumps. For this example, we will add two new jumps to the table, one from cell C to cell E and one from cell D to cell B. After the next move from cell D to cell B, we can again add two new jumps to the table, one for starting cell D and one for finishing cell B. Instead of letters in our implementation, we will use cell locations as we did before. This is how our table looks like for the sample test after each instruction. So, now the robot can skip a segment of previously visited cells by jumping to the next free cell right away. For example, after the fourth instruction, we already know that if the robot goes from the cell 1, 2 south, it will stop on the cell 3, 2. Let's implement two new functions, jump and add jump. We will use jump to move the robot and add jump to update the table when the robot stops. After each instruction, we will add two jumps to the table, a jump from the previous cell in the direction of processed instruction, and a jump from the current cell in the opposite direction. Now, we still have some instructions that take longer to execute. But such situations are rare, and on average, we spend big O of 1 for each instruction. Overall algorithm time complexity is big O of n. Thank you for watching. Be sure to check out the analysis on the problem dashboard. Now I'm going to hand it over to my colleague, Yizhen, who is going to walk you through the next problem.
Hi everyone, my name is Yizhen and I'm a software engineer at Google. Currently, I work on Google Pay team based in Singapore. I participated in Google Code Jam and Kickstart when I was a student. We hope you enjoyed practicing the Kickstart problem on our platform. Today, I'm going to walk you through the GBus count problem. First, let's go through the problem statement. There exist some cities that are built along a straight road. There are n GBuses that operate along this road. For each GBus, we know the range of cities that it serves. The ith GBus serves the cities with the numbers between AI and BI inclusively. For a subset of cities from the query, we need to find out how many GBuses serves that particular city. Before jumping to the problem analysis, let's sort out some of the common mistakes you might have when you're trying to understand the problem. The GBus serves the city with numbers between AI and BI inclusively, which means AI and BI are also included in the serving range. Now, let's start analyzing the problem. Let's try to use a simple example to visualize the problem. On the top, the dots represent the cities in a row. Below them, each line segment represents the serving range of a certain GBus. To simplify the problem, let's first assume that we want to query the number of GBuses for every one of the cities, from left to right. At city 1, there is only GBus A, so the total number of GBuses is 1. At city 2, it is still inside the serving range of GBus A, and we have GBus C joining, so the total number of GBuses is 2. At city 3, it is inside the serving range of GBus A and C, and we have GBus B joining, so the total number of GBuses is 3. At city 4, we are out of the serving range of GBus A, while we are still inside the serving range of GBus B and C. Therefore, the total number of GBuses is 2. At city 5, we are out of the serving range of GBus B, while we are still inside the serving range of GBus C. Therefore, the total number of GBuses is 1. Based on the simulation above, we have some observations that when scanning through the cities from left to right, for each of the GBus, first, there will be a certain point where the GBus is starting to contribute to the total number of GBuses. This certain point is the left end of the GBus serving range, which is AI. And there will be another certain point where the GBus is out of the serving range and it will never come back again. This certain point is one city to the right of the right end of the GBus serving range, which is BI plus 1. So here comes the solution. For each city, we maintain the total number of the GBuses whose left-hand point is at this city. For simplicity, we use xi to represent this number city I, and we maintain the total number of the GBuses whose right endpoint is one city to the left of this city. Similarly, we use yi to represent this number of city I. Then we can simply scan the city from left to right, because even in the large dataset, the maximum number of the city number is 5,000. For each city, we add xi to the total number of GBuses, which means the number of GBuses that start to contribute to the current total number at this point. And we subtract yi from the current total number of GBuses, which means the total number of GBuses that finishes contributing to the total number at this point. After that, for each city from the query, we just output the total number pre-calculated for that city. Now, let's take a look at my C++ solution for a better understanding. First, I use start bus count and end bus count for calculating the number of GBuses that have the start point and the end point separately in that city. Then, I scan through the cities from left to right. At each city, I add the number of GBuses that start at that point and record the results. After recording, I subtract the number of GBuses that end at that point from the current number, so that the future cities will not have those GBuses that already ended at this city. Finally, for each of the query, I output the total number that was pre-calculated for that city. That is all for me for the GBus count problem. Be sure to check out the full analysis on the dashboard. Next, my colleague Phil is going to explain the final problem in today's session. Thank you.
Hey everyone, I'm Phil and I'm a software engineer at Google. Here I work on quantization and applied information theory for nearest neighbor search. In high school I did USCO and code forces, and today I still participate in a few programming competitions while helping out with the ones that Google runs. Today I'm going to walk you through the problem Sherlock and Watson Gym Secrets from 2016. Let's begin. This problem is at heart a number theory problem. We're given two exponents a and b and want to find the number of pairs of integers such that the first integer raised to the 8th power plus the second integer raised to the bth power is a multiple of k. Whenever I solve a problem, I make sure to look at the input constraints and know anything that stands out. In this problem, I noticed a few things. First, k is allowed to be 1. This is tricky because we're looking at numbers modulo k, and we generally think that anything raised to the 0th power is 1. But if k is 1, then a number raised to the 0th power of mod k will be 0, not 1. Additionally, the first integer in the pair I can't equal the second integer j, and both of them must be positive. We'll deal with this later, but we can first ignore the I can't equal j constraint and later subtract out the cases where they are equal. Finally, n can be very large, up to 10 to the 18th, but can also be less than k. The first tool that came to mind when I was solving this problem is exponentiation by squaring. The exponents we're given, a and b, can be up to 1 million, which is fairly high. Naively, that would require doing around 1 million multiplications. Exponentiation by squaring reduces this from a linear complexity in the exponent to a logarithmic one. For example, if we want to compute a number raised to the 8th power, we square it 3 times instead of multiplying it by itself 7 times. This technique generalizes to any exponent, not just powers of 2, and the logarithmic complexity it gives is key to implementing a fast enough solution to this problem. With that out of the way, a brute force approach to this problem is pretty simple, and it's generally what I start out with. I often approach problems looking for any correct solution, even if they're not fast enough, and try to iterate upon that. So for this problem, we iterate over all pairs ij and check if each one satisfies the criteria. This would take n squared times log a plus log b time, because there's n squared pairs, and each one takes log a plus log b time with our exponentiation by squaring technique. So n squared is far too high because n can be up to 10 to the 18th. We can optimize this technique though by realizing that when we loop over I, the first integer in the pair, and then loop over j, the second integer, to process all the pairs, the inner loop over j is being repeated over and over again. For any I, our goal is to find j such that j to the b mod k equals minus I to the a mod k. This way, when we add them together, we get 0 mod k, which means the sum is a multiple of k. We can pre-compute these j instead of recomputing them every single iteration of I by storing them in an array, which we'll call L. Then, for each I, we just look up the appropriate entry in L. This turns our quadratic time routine into a linear time routine. One thing to watch out for is that if I to the a plus I to the b is a multiple of k, we have to subtract it out of our results, because as mentioned earlier, I cannot equal j. Even something linear in n is too slow though, because 10 to the 18th is a very large number. So we have to optimize this further. Here we use an insight from number theory that going through all integers from 1 to n is actually going to repeat once we get to k. Just looking at the integers from 1 to k is sufficient, which gets us a k log a plus k log b solution, which is fast enough, because even though n can be up to 10 to the 18th, k is bounded by 100,000. So this is a fast enough solution, and this is what we'll be implementing. To implement this solution, I started off by writing a modular exponentiation helper function. This uses exponentiation by squaring as mentioned before. It also takes care of the case where mod equals 1, the edge case I mentioned earlier. And while it's not relevant for this problem, in other ones you may have to watch for how your code handles 0 to the 0th power and the desired behavior there, because in general 0 to the 0 is not well defined. I use a recursive implementation because I find it easier to read and reason about, even though generally an iterative implementation is considered slightly faster with a lower constant factor. So after this helper is the primary code used to solve this problem. And so first I read in the inputs and compute the array L, and notice the usage of mod m everywhere, where m is 10 to the 9th plus 7. So this constant is specified in the problem statement because the number of pairs ij is so high that instead of outputting the number of pairs directly, we output it modulo m. And so just like in the problem statement, we use this modulo m everywhere in our code to prevent overflow. Otherwise, we'll get integer overflow and our answer will be incorrect. In the final step, we compute I to the a and look up negative I to the a in L to accumulate in our answer. If I to the a plus I to the b is a multiple of k, we subtract it to avoid counting this case that's not allowed in the problem statement. The final bit of code here is the simple main function that calls our code above. I generally prefer to separate the main logic that solves the problem from the actual main function because it reduces the chance of me setting state in a previous test case that I forget to reset in a later one and leading to bugs. So this is the entire implementation, and that's how you solve the problem. So this concludes the problem walkthroughs for our coding practice with Kickstart session today, and we hope you had as much fun as we did. Let us know in the comments, and Lizzie is going to close us out. Over to you, Lizzie.
That's it for problem walkthroughs today. Thank you for your great engagement and participation. If you have any remaining questions, be sure to ask your peers in our Facebook group, where you can connect with the community and receive latest updates about Kickstart. In addition to this video, be sure to check out our full analysis on the dashboard, which you can find by clicking on the View Dashboard button at the top right of this page. When you get to the dashboard, select whichever problem you'd like to review, and then click on the Analysis tab. You will also be able to download the input and output files at the bottom of the page. Finally, be sure to check out our schedule page at g.co/kickstart and apply what you've just learned in our upcoming rounds and future practice sessions. Each round starts fresh, so you can participate in as many rounds as you're able to. The more you practice, the more you'll improve, so why not give it a try? And that's it. Thank you again for taking part in coding practice with Kickstart. Hope to see you in future rounds. We hope you had fun. Until next time, bye!